For problem 3, we will have infinitely long wire. This wire is infinitely long. It is positioned at xd, and current I is flowing into the page, which is minus IZ direction. So this is the wire. Current is flowing into the page in minus IZ direction. I remind you that X, Y, Z follow the right-hand rule, which means that you take your right hand. I use my left hand because you see my mirrored image. You use your right hand. You put your fingers along X. You bend them towards Y, and your thumb shows you direction of Z. So Z is out of the page. This is the direction of Z. X, Y, Z follow the right-hand rule. But the current is in minus IZ direction. It goes into the page. Okay. This wire is centered at, the center of this wire is at XD, and it has radius W. The radius of this wire is given, it is W. The current is uniformly spread over the cross-sectional area of this wire. For part A, we need to find if the center is located at XD, find the X and Y components of the magnetic field at point X0, YH. We need to find X and Y components of magnetic field at this point. What will be the picture of the lines of the magnetic field? I already draw this pink circle before we started recording to avoid this pleasure drawing the circle in front of you. So, how to figure out what will be the direction of the line's magnetic field? First, we understand this is infinitely long wire in the direction perpendicular to the board. So the lines of the magnetic field will be circles. The question is, what will be the direction? You use your right hand, you put your thumb along the current, you bend your fingers, and your fingers show you the direction of the magnetic field. So the magnetic field for this current will be clockwise. Now, the lines of the magnetic field are tangential at each point to this circle. So the direction of the magnetic field at the point of interest, X0, YH, will look like this. This is the magnetic field at this point, and we need to find X and Y components of this magnetic field. Okay, so first of all, I suggest that we find magnitude of the magnetic field, the length of this vector, and then we will project it in X and Y. We will use Ampere's law to do that. I remind you that this wire is infinitely long, which will allow us to simplify the left-hand side of Ampere's law. Ampere's law, integral B dot dr, closed loop, is equal to mu naught current enclosed by this loop. Left-hand side, B times 2 pi r. What is this r? It is radius of this loop that going through the point of interest, X0, YH. This magnetic field is created by this wire. B times 2 pi r is equal to mu naught, current enclosed, current is I, and we found the magnitude of the magnetic field, magnitude created by this wire. Now, so we know the length of this vector, and what they ask us to do in part A, they ask us to find X and Y components of this magnetic field. So we need to introduce angle. Before we even start breaking B in the components, we need to figure out what is R. So let's write what is R in terms of what is given. R, I will draw it. This is my R, and this R from this right triangle is square root of D squared plus H squared. R is square root of d squared plus h squared. Now I need to find b sub x, and b sub y. This is b. Okay, so what will be b sub x? I need to introduce angle. Which triangle I will use? I will use this right triangle. And angle that we will be using will be, let's say, this one, angle with horizontal. I call this angle theta. So b sub x, x component of the magnetic field, will be magnitude mu naught I divided by 2 pi r, where r is square root of d squared plus h squared, times cosine theta, What is cosine theta? So to find cosine theta in terms of what is given, we need to figure out which angle is theta and in our original right triangle. And we know that if we have two right triangles, angles between perpendicular legs in these two triangles are the same. So my angle theta is between this horizontal and this tilted leg. So in my new triangle, which leg is perpendicular to horizontal? It is vertical. Which one is perpendicular to this tilted one? It is this one. Then this angle is the same as this angle. This is also theta. Now let's express cosine theta in terms of what is given. What is cosine theta? Cosine theta is adjacent leg, which is h, divided by hypotenuse, which is r, which is square root of d squared plus h squared. And my final expression for the x component of the magnetic field will be mu naught I divided by 2 pi. Cosine theta will give me h here, and then square root of d squared plus h squared, another square root will be, I will end up with d squared plus h squared in the denominator. This is x component of the magnetic field. Now what will be the y component of the magnetic field? By. For by, I take the length mu naught I divided by 2 pi r, which is square root of d squared plus h squared, and I need to multiply this by sine of theta. Sine theta. What is sine theta? Sine theta is, from my original triangle, sine theta is opposite leg, which is d, divided by hypotenuse square root of d squared plus h squared. And my final expression for the b component of the magnetic field will be by is equal to mu naught I divided by 2 pi square root and square root d squared plus h squared in the denominator, and we don't forget d in the numerator. This is y component of the magnetic field at this point, and this is x component of the magnetic field at point x0 and yh. For part B, we will have two wires. So one the same as we had in part A, and we already found the components of the magnetic field created by this wire at point 0h. This is point 0h. So this magnetic field created by this wire that we found in part A looks like this, and we know both components. And now we add second wire. Current is also into the page. The lines of the magnetic field will be also circles centered at the wire. And now I need to find the direction of the magnetic field created by this second wire. So how do we do that? You use your right hand. I use my left hand because you see my mirrored image. So I put my finger, you take your right hand, you put your finger along current, and then you bend your fingers, and your fingers show you the direction of the magnetic field. So the magnetic field created by this left wire will be clockwise. Now this is B right. B, I put R for B right. This is B left, B left. And now let's look at this picture. So since currents have the same magnitude, these two lengths are the same magnitude of the magnetic field created by left and right wires are the same. And we immediately see that from symmetry, Y components of the magnetic field cancel each other. Now we look at these lines of the magnetic field created by left and right wires, and from symmetry we immediately see that Y components of the magnetic field created by left and right wires cancel each other. So net Y component By will be 0. X components have the same magnitude, and I just take X component created by of the magnetic field created by right wire, this B sub X, B total X component will be twice of the magnetic field, X component of the magnetic field created by this right wire. I put 2 here, and then mu naught I H divided by 2 pi a d squared plus h squared, and 2 cancel out, so my final answer is mu naught I h divided by pi d squared plus h squared.